welcome. Okay, it should be cleaner. So welcome everybody on our second lecture. Unfortunately, I got a notification from our dean that for now we stay online. I did have a bit of a clash with him, but unfortunately his decision stays. So we are going to continue. We need to continue remote learning and remote meetings. I don't know, maybe it will change during the semester, but I don't know. I lost my hope, to be honest. We'll see. Anyway, for now we stay online. So next week we meet online. Again. So let's continue. Let's go back to our lecture. Any questions, maybe?
Did they give you any reason why do we have to continue online?
Could you repeat the question? Because I have
if they gave you any reason why we have to continue online?
It gave me the reason that there are some people in the group that are having one of the lecture today where they are enrolled more than 30 people. So there is one lecture with 32 people enrolled. And some of you are enrolled in this lecture as well. And because of this, because one lecture must be remotely, because there is this rule of 30 plus groups that need to be online, then unfortunately all the other lectures during the day for you for the group are online. I don't understand this. For me, it's a very bad decision. But anyway, I can do really nothing. So
okay, thanks.
I did my best. Really, believe me, I did my best to revert this decision. And unfortunately, half of my lectures stayed online without really much sense. It happens, as they say. Hopefully during the semester it's gonna change. But is it gonna be this week, next week, or in June? I don't know. Unfortunately, so far we must continue in this version. Yeah, let's continue then. Before we go to ARM, because today we begin ARMs, ARM microcontrollers in greater details. Again, I gave you a hint about them already previous semester. So today we start to talk about them more seriously. What options do we have and what's inside and so on. But before this, one last thing, which is the benchmarking. One small thing about the benchmarking, because it requires to be said, but it's not very important anyway. But because we'll be using benchmarks throughout today even, then comparing the various cores, ARM cores that are available. Thus, a few explanation about it. So benchmarking, of course, is used for speed comparison of microprocessors and, to much less extent, microcontrollers. Problem is that it's written here that comparing is difficult as always, and comparing of microcontrollers is even more difficult. This is very much of the analogy with the computers. So we can compare the microprocessors, so between Core i7 something, Core i7 something else, Core i9 or AMD, Ryzen something. So we can compare them, but of course this comparison is not very truthful. And in case of computers, PC computers, there are plenty of various benchmarks basing on office applications, on games, various kinds of games, and or on scientific calculations, various kinds. There is a comparison done of the microprocessor. So the main unit plus the cache, plus the memory, plus the main board, and so on. So already in the PC computers, which is pretty much standard, you can see how many you can find it. Even if you're not aware, you can find it on the net. how many different benchmarks are being used for comparison, giving pretty various results between the platforms. So even if in one benchmark one platform wins, then in the other one it fails. In case of microcontrollers, the situation is that more difficult. That first of all, we are not so much interested in the raw processing power, but quite often in case of microcontrollers, we are interested in real-time response very often, and or we are interested in the lowest power consumption or in the low budget power processing power to power consumption ratio. So basically, we are interested in, of course, in a bit other, in a various completely different areas, completely different parameters. And additionally to comparing microcontrollers to these problems, we are using microcontrollers in a very different way in our application. Sometimes we need the microcontrollers for calculations of camera data, and sometimes just for switching LEDs. Different resources are necessary, and thus comparison is a bit is challenging because it's really very much application dependent. For this reason, there is really no true benchmarks or real benchmarks comparing the microcontroller part. The only benchmarks existing and used are for comparing the microprocessor plus the memory. So it depends on the benchmarks. So there are a couple of use of those used you have now on the screen. So the basic one, the clock rate. So comparing the clock rate between various microcontrollers, of course, it is useful only if we compare very, very similar microcontrollers, so same architectures, yet with produced, for example, in different technologies, so that we have a technology allowing 16 megahertz clock, another technology allowing 32 megahertz clock. So all in all, if we compare the clocking, so the newer will be better. Pretty obvious and pretty useless normally, or trivial. Useless, maybe useful it's a bit, but pretty trivial. More useful metrics that is sometimes found for comparing microprocessors is the MIPS metrics. The MIPS, so millions of instructions per second. This works pretty well in comparison of between RISC microcontrollers and RISC processors. Again, it's not. It's really about comparing cores. So for in case of microprocessors, 8-bit and RISC microprocessors, if you would like to compare between various of them, then it may work, so it may give you some information, but using the MIPS to comparison between the RISC and CISC tape, even 8 bits in both cases, is futile. It's futile. So comparison of STM8, for example, with 80 mega or PIC micro might lead to false results. Besides, in case of CISC, the problem is that the instructions require a various amount of clock cycles depending on the addressing mode. Depending on the addressing modes used, in RISC we have non-addressing modes, so everything is inherited in the instructions and single cycle usually. In case of CISC microcontrollers, it's not single cycle, and for MIPS calculations, of course, it's the most convenient to take single cycle instructions like NOP. So usually we have in MIPS everything basis on NOP instruction. Yeah, of course, but NOP instruction does nothing, so it doesn't give us very much of information. So MIPS is a bit better than the clock rate comparison, but still only slightly, only a bit. Then we got the metrics comparing the floating point capabilities of the units, and this is actually the metrics which works pretty well and delivers us substantial information about how well the floating point unit is being implemented in microcontrollers. If we compare microcontrollers with the with existing hardware coprocessor, floating point coprocessor, in other words, floating point unit, then this tells us about the construction of this internal construction of this unit. But if we compare the software algorithms, so how many floating point calculations can be done without use of the hardware coprocessor, just by the means of integer CPU, then also we have an information about the performance of the microcontroller, of the memory around the microcontroller during the calculation of during floating point calculation. This matrix of millions of floating point operations per second, so that's where the name comes from, has a sense because the floating point operations are being standardized by IEEE 754 regulation. So we talked about it already during introduction to microcontrollers. So you should remember how many operations are basically necessary during even simple adding or subtracting. Yeah, the operations are integer all in all, but there are a lot of operations, a lot of integer operations that has to be done in order to perform this floating point, single floating point operations. But it is standardized. The most important is that it's standardized, and the floating point is always 32 bits. So we are using single precision most of the time, double precision sometimes, but mostly single precision, which means that on various microcontrollers, the implementation tends to be similar, and thus this matrix actually is pretty useful. In order to avoid the problems with platform-specific comparisons, there are two matrices for comparing of CPUs, of integer CPUs, basing not on comparison of plain hardware parameters like the clock rate, but rather on some artificial program, on some artificial algorithm. And these are two such metrics. So this is Drystone MIPS and CoreMark. So quite popular metrics. The Drystone was first. This is a code, a small code that if you want to run it, so you just compile it with your compiler and run it on your CPU. In case of CoreMark, it's more or less the same. It's also a code, pseudocode that needs to be implemented onto the CPU tested. Yet, so theoretically, the idea is the same. The difference is that Drystone was introduced to the market already some time ago, and then nobody thought about the cache, for example, in microcontrollers. Today, the cache is nothing really different in case of peripherals or internal elements of the CPU or microcontroller, because cache we can classify to CPU, or it's somewhere in between. Anyway, nobody thought about it then, and Drystone code is too short a bit and too sensitive to optimization as well. So also the second problem of Drystone, besides that it fits in the cache completely, there is a cache in microcontroller, and then we are starting testing cache and not program memory. But there is also a second mechanism. Thus, for this reason, a CoreMark was introduced, which is an improved version in general of the MIPS, and is used more and more often today. In case of those two matrices, they deliver the units of that we get after such tests are some value by megahertz. Mind that. So again, that's different because here we have just a value only, so some 20 MIPS, for example, or 50 flops. While for Drystone MIPS, we've got sometimes we also have DMIPS, but more and more often is DMIPS per megahertz. In case of CoreMark, it's CoreMark, how many CoreMarks per megahertz. It's also did change a bit during the years in order to be able to compare various efficiency of various structures, of various architectures. Again, this changed because many times ago many years ago. All the microcontrollers were clocked 16 megahertz, 20 megahertz. Just 24 was really high, but usually it was between 12 and 16. And for many years it was this. It was simply it stayed at this between 8 and 16, let's say, and then you could compare the performance. Besides then, the sheer processing power was on the top, so the faster the better. Today this changed a bit, so sometimes we need really the fastest, sometimes we need the most efficient. So sometimes today we have a capabilities to use 400 megahertz processors without a problem, for a clock for 400 megahertz, yet we are using 40 megahertz, 60 megahertz, 20 megahertz clocking because we don't need it. So in case of embedded systems, it's not always the sheer processing power that's important. That's why the dry stone nowadays, they are benchmarking are usually in the units of MIPS per megahertz or per marks per megahertz units sometimes. Okay, that would be it about the few remarks about the benchmarking. Now let's move towards the our main core issue today. So back into the world of ARM. So ARM cores and ARM-based microcontrollers, because that's in common. ARM cores. Let's go. Yeah, an introduction was already given by the end of last semester. For those that do not remember, the ARM is a 32-bit RISC instruction set architecture. So RISC ISA developed by ARM Holdings. So this company was in the 1980s. Was focused on producing microprocessors and chipsets for computers. For example, Commodore, very popular at those times, Commodore 64, had a processor that was 6502, 6510, it was 8510 for Commodore 128, Atari. So those computers at those times were very, very popular computer for homes. So they revolutionized the market. So PC computers were just for business, and for normal users, for home users, only this kind of small computers were used, and the computers were constructed based on the processor, physical hardware, delivered by this company or by the ancestors, by the people that by the founders of this company. Anyway, in the 90s, the holding itself, so the companies inside the holdings decided to, or the leaders decided to go another way, to try to introduce to the market an architecture, a software architecture, and then license just this architecture, but not to deliver the microprocessors themselves. So that was the idea of licensing, of leaving of the licenses, of not building anything by themselves, but of leaving of the licenses for the instruction, for the architecture itself. And this turned out to be pretty much of a success. So it took us some time. It took us, yeah, the ARM is Acorn RISC Machine. Yeah, this was the name of the company. So that's where the ARM came from. So Acorn RISC Machine. This was pretty much of a success because this idea of a microprocessor based on the instruction set architecture, it was under heavy development through the 1990s and through the first decade of millennium, mainly the 1990s. It was the time of heavy development, under the development that the market was living differently. The ARM processors were not on the market yet, or were not noticeable on the market. Yet they were under heavy development, and it turned out that this was a good path. So this was a good way, because today 90%, I think even today, more than 90% of all 32-bit microcontrollers that we have on the market are including the ARM core inside. So really, the ARM revolutionized with this idea, and with their architecture, did revolutionize the world. The large changing factor was one of the largest changing factor was the onset of the cell phones, to be honest, because that's where this is the moment where the development of or the history of the ARM sped up with the first iPhone, and then with all the other brands trying to catch up with this idea, with the processor that is powerful yet low power, so capable of servicing the complexity or required complexity, so the heavy calculations present in cell phone, yet low power enough to be portable, to be small, to be cool, simply cool. And the companies failed, to be honest, the other companies. So there was a time around maybe 2-3 years after the onset, the beginning of iPhone 1, where the other companies like NVIDIA, like Texas Instruments, like even Intel, they were trying to deliver their own architectures, the processor based on their own ideas, as being the main CPUs in cell phones, but the ARM still dominated. So the ARM architecture, so first ARM9 and ARM11, because this were the architectures that won the world, and then the last blow came from the Cortex-A, so from the Cortex family and Cortex-A, especially in the case of application processors. So this blow was deadly, to all the ideas about the cell phone. And today, cell phone only ARM-based, applications. So only notebooks and desktops. We have other kind of processors. And of course, in a very small embedded systems, because in a parallel to the large application processors, let's say, destined for the cell phones, in development was the families for smaller microcontrollers. So the idea about the ARM was to deliver the portfolio for embedded systems of various sizes. So from the very tiny ones, even close to the 8-bit world, so tiny, so small, up to multiple core beasts, looking like a cell phone and having complicated calculation requirement. And yet they succeeded. So nowadays the portfolio is pretty much complete. It's so complete that everybody in the world is using ARMs right now. So this is just a piece of, there are just a few of the families using the ARM cores in their portfolio. Interestingly, IBM, Intel, Texas Instruments, it's shown here, the Infineon, Philips. So today the Philips is it's NXP. Motorola, which used to be until the last days it was using, so right now it's not existing anymore. In fact, this division, because it's bought out by Philips. Philips is existing, but semiconductor part. Nowadays it's NXP, and it's after multiple reconfigurations. It is a combination of former Philips semiconductors and Motorola processors. Anyway, even the largest companies having their own, so like Texas Instruments and Intel, so the companies that originated in the 1970s, the market of microprocessors and signal process and microcontrollers, because Texas Instruments delivered the first microcontroller into the first microprocessor to the market. and they still are very large companies, and they do still have a lot of various cores in their portfolio. But more and more cores in their portfolio are based on ARM. It's especially visible in case of Texas Instruments. Intel, of course, is basing pretty much on staking pretty much on desktop computers, PC computers, so they have their own x86 platform, which they rely heavy on. But the Texas Instruments also delivers their own solutions like C2K or C6K DSPs, but the amount, the number of ARM based microcontrollers, so the microcontrollers that they include at least one core ARM core inside, is growing has been growing every year. In general, what's the idea about the ARM? So there are really a couple of interesting things in this architecture. So they choose another way a bit from what was on the market in 1990s, 80s and beginning of 1990s. So from the start, the architecture was 32-bit. This was a revolution kind of in 1990s because you remember this was 1990s, 80s and 90s. It was a time of 8-bit microcontrollers. In case of processors for CPUs for computers, yeah, the computers were 32-bit, but 32-bit we talk about clocking like 40 megahertz, 60 megahertz this time, 80 megahertz. So there were architectures like 286, 386 from Intel, 486, 66 megahertz, 486, for example. Yeah, it was a beast, I must tell you. But this was the time, and microcontrollers, nobody really thought about the 32-bit microcontrollers in 1990s, but ARM did. ARM did from the very beginning. They started from the very beginning. They started with the 32-bit construction with the architecture that was from the top to bottom 32-bit. Today it's a problem, as you will see later on. Because today some people would like to use 64-bit, right? Intel is having 64-bit support, so ARM should have 64-bit as well. But then this history becomes kind of a problem, kind of an issue, because everything is 32-bit from top to bottom in the microcontroller. But going through history, not through the through current times, in the history, this was good. This was actually pretty good. From the start, this was risk. From the start, this was risk with the technology of VLAW, so very long instruction word support for this technology, meaning that it was possible from the beginning to get from the memory more than one instruction in one reading cycle. Not one. Again, historically, at this time, the microcontrollers, either like PIC microcontrollers allowed reading one instruction per clock cycle, or like various CISC type microcontrollers required reading an instruction in a few clock cycles, 2, 3, 4, depending on the length of the machine code. And this was again a revolution, the VLIW, so very long instruction word, where this all instructions were 32-bit long, constant 32-bit. So everything was 32-bit. So the instructions were also 32-bit long, exactly. Yet it was possible to get, for example, 4 or 8 instruction in one reading clock cycle, thus reducing the problems with slow program memory. Flash or EEPROM is slower than SRAM. And if you want to get beyond, if you want to get beyond 50 megahertz, in fact, you need normally to slow down the microcontroller in accessing the program memory. With the VLIW, you didn't need to, because you could get slower. You could read the memory slower, but then unpacking the instruction and processing them became simple. So very long instruction word technology almost from the start in here, thanks to this 32-bit architecture, thanks to this risk idea, so that everything is risk, so really reduced amount of number of instructions and simple instructions. In the very beginning, von Neumann was there. So the architecture where the data and instruction bus is common. So this was there, but in a very short way, in a very short time, even before reaching the market. In fact, turned out that von Neumann misnogged that they needed to turn to modified Harvard architecture. So we split data and instruction bus. This helped to deliver the pipelining. So we talked about it last semester because it's already even in STM8. So when we talked about the STM8 in the beginning of previous semester, but the pipelining in general, the main role of pipelining is to increase the performance, to keep the internals of the CPU busy all the time, even doing different operations. It does require, it works best, I would say, with Harvard architecture, where the data and program bus are split, and that's why most probably they changed from von Neumann, which is originally there, to Harvard, which is dominating today. Modified Harvard, which is dominating today, together with the pipeline. So this was from the beginning. And throughout the history, a lot of effort, of course, was put by the company, by the ARM holding, to deliver the course, to deliver the ISA, the architecture, instruction set architecture, and the descriptions of this architecture. Yeah, everything started in the end of 80s, and it went through the 90s with various documents appearing. So various documents appearing where the structure, so many important elements were added in those documents, and not in the beginning. The documents and the processors were just internal, I would say, internal units, like was the case for the description of version 1 of the documentation. Version 2, so families ARM1 and ARM2 were basing on could be built, I'd say, could be built based on this, on the description in the documents version 1 and documents version 2. They weren't. More important is that there were feature added with each new document appearing, set of documents appearing. This is like a standard. So it is not a standardizing organization. This is just a private company, so now owned by by some Japanese fund, as far as I know, but a British company, by the way, because it's British, owned by Japanese fund. So it is not government official. That's why these are not standards. But practical point of view, these documents could be treated as standards. Having in mind that today ARM is everywhere, virtually everywhere, with the IoT. So for sure you have ARM microcontroller in your backward pocket or on your hand. So we have in the first versions, only 26-bit addressing, no hardware multiplier. Then they added 32-bit multiplying instructions. Coprocessor support was added. Then there was added a cache. Still, we talk about 1990s. Then in 1990s, 25 megahertz, but only 12 MIPS available at this clocking frequency. At least theoretically, it was possible, because usually the commercial unit was weaker than the maximum theoretical value given during simulations, obtained during simulations. Then version 3 of the architecture includes already the ARM6 and ARM7, so the commercial units. So there were some processors based on ARM6, ARM7, although it's end of 1990s as far as I remember, and they were not that popular, I'd say. So at least I wasn't using them. So maybe in some circles they were popular, I don't know, but not in my circle, professional circles. 32-bit addressing already there, cache, coprocessor, and memory controller, first things, with the clocking rate exceeding 50 megahertz. So fantastic speed comparing competitors this time. And then came architecture version 4, so the first useful architecture. First commercial success came from this architectures with the family of ARM7, TDMI8, ARM8, and ARM9 with even 5-stage pipelining, and not 3-stage, which is the standard, but 5-stage pipelining with loop prediction, with memory management unit, so for operating system, and memory protection unit for some kind of security, with the special 16-bit instruction set. 16-bit, take a look, in 32-bit microcontroller, 16-bit instruction set. PIC 18 has 18-bit instruction set, and this is 8-bit microcontroller. And here in ARM version 4, they thought, let's simplify something. So let's simplify instructions. Let's make them 16-bit. Whoa, and they did, and it succeeded because in fact, as you will see in a moment, this was not such a bad idea. 16-bit instructions in 32-bit microcontroller, all in all. Up to even 200 megahertz and 200 MIPS possible theoretically. It was a popular version at those times. So, and mid 1990s, end of 90s, beginning of millennium, and even more success came with the next family, so version 5, with the increased pipelining, 6 and 7 stage, with the onset of ARM9 improved and ARM10, and this is the time, if I'm not mistaken, this is the based on these families were the first cell phones, smartphones, not smartphones, because of course it's about smartphones. For smartphone usage, they were added the 16-bit instruction set. This was more about code density in microcontrollers branch, but there was added Jazelle instruction set, which means hardware support for Java. Android is based on this. So hardware support for Java, hardware support for signal processing. Cell phones are based on signal processing, multi-level cache possible here, and the throughput 1000 MIPS at about a gigahertz. So still not the levels we can see now, not the levels we can see today, but already pretty nice. So it's the first decade of the millennium. So it's the first decade of the millennium, version 5 of the family. And then gradually version 6, with the major improvement being the ARM11. ARM11 being the stronger brother of ARM9, because it turned out that ARM10, I didn't know any processors based on this software, on this core description. Mind that not all core descriptions that ARM introduced to the market, not all core descriptions became successful. So not all core descriptions that ARM described were implemented, in fact, in larger number of units. And ARM10, from my knowledge, was one of these families that were not really used, and Cortex-M1 from this, for example. So there was such an idea of using Cortex-M1 in FPGA, because this is this kind of family. Its final market is the FPGA, but it never came to fruition, in fact. But what came to fruition, what became successful, is the ARM11 and Cortex-M0. But the ARM version 6 family is mainly about ARM11, so stronger brother for an improvement towards faster cell phones, smartphones, mainly. So more pipelining, 8 and 9 stage, time to, of course, the Jazelle DSP, but the new thing which appeared was the SIMD. So the optimization, in fact, for audio and video applications, SIMD is a single, of course, instruction with multiple data. So working on pictures, working on graphics, so something that we really need on those beautiful, colorful displays of the smartphones, and it was there. It was included in version 6. And then we come to the present time. So the present time, almost present. So version 7 of the architecture is the version that is still, the production is going on very much of the course. It's just that nothing new appears there, nothing new in this family. So Cortex family, this is not true. So it's a Cortex family, not without M0, because this is the Cortex family, a part of the Cortex family right now. So this was true a couple of years ago, but today we have version 8 of the description. So version 7 against the documents, the standard version 7, we've got major part of the Cortex family, but not all. So the newer Cortexes, like Cortex, the newest from Cortex M family, like M35, 33, 35, 55, or R7, R8, or A15, they are or following the specification version 8. In version 7, we've got the original breed of Cortex microcontrollers. Original breed of Cortex M, Cortex R, and Cortex A. We'll talk about it already after the break. Yet the major capabilities are about increasing even further the pipelining. So it's 13 stages pipelining this time. Even not 3, not 5, not 9, but even 13 stage pipelining. Such a long pipeline, of course, for keeping busy, for keeping all the resources busy, and for improving the performance. Naturally, the TAMP2 Giselle DSP, so this was before hardware support for divide and multiply of integer and floating point numbers, and the multi-core. This was actually pretty new. So instead of a single core, the era of a multi-core units came into existence. Of course, the multi-core is a problem with cache, the problem with interrupt sharing, the problem of resource sharing, the problem of synchronizing the code, because this is for multiprocessing, has certain problems connected with it, so they have to be solved, and they have to be. This solution was given that with Cortex A multiple core, Cortex A, and Cortex R multiple core. In case of microcontroller cores, so Cortex M's, then we don't, unfortunately, thus far we haven't received a multi-core solution. Even in the current description, in the current document, which is the 8th version of ARM. In this 8th version of ARM, they appeared two major new things. Of course, many new Cortexes appeared, so now it's really so many of them that even I lost my trace in case of all the options that I have. So more or less I know, but I don't know in 100% of the versions. I have more interesting things to do, but the two major features were added compared to the previous version 7 of the architecture. First of all, the cryptography. The crypto part, it turns out that the complexity grows of the embedded systems, and the embedded systems based on our microcontrollers and the cell phones became very vulnerable to various attacks. Today we live in a digital world, and everything is connected. So if everything is connected in a certain way, then it means that remotely there are people that are for money or for free and may damage our property in this way. So the security, the cyber security, as you call it, became very much of an issue, and is very much of an issue today. Therefore, in the 8th version of the architecture, a lot of effort was put by the company to deliver solutions protecting the access to various parts of the microcontroller, and making the microcontroller independent or immune. Immune is the good word to various attacks. Again, if we have some time during the semester, we will. I have lectures prepared about this security features, but we'll see. We'll see how it goes. Second important improvement in this architecture was the appearance of the 64-bit support. So double precision floating point support, and also 64-bit numbers support. So normally, again, the microcontroller itself is 32-bit from the top to bottom. So it was added yeah, it's just a plaster on what on the current architecture. So there was no revolution here. And besides, from our perspective as microcontrollers users, it's out of our it's still out of our range, because it's this 64-bit support was added. So this ARC64 was added only in the world of application processors, not even in the world of DSPs, and now in the world of microcontrollers. Okay, that was the those were the major remarks about the history of the ARM. Now more about the units, more about the options that we have in the ARM world, the options in case of not the architectures, not the documents, not the standards, but about the units themselves. So what options, especially in the microcontrollers world, do we have? But that's already after a break. So let's have a 15 minutes break and we'll be back after this. So welcome again after the break. Here we can see the very nice colorful picture showing us the options we have in case of cores, the cores themselves. So the software architectures sorted a bit against the performance and against more or less against the capabilities and against the history. So the time, because this is not up to scale, but in but in this direction we've got the time scale. So what can we see here? The history of microcontrollers began with ARM7. With ARM7 core, and the ARM7, especially the ARM7 TDMI, was the core, is the ancestor actually of our existing currently all Cortex-M microcontrollers. So there were a lot of microcontrollers, 32-bit microcontrollers based on this cores available in the market during late 1990s. Those processors were pretty decently spec'd compared to the existing competition. So we talk about the Atmel and Microchip, mainly microcontrollers, so significantly slower comparing to the ARM7. On the top edge, there were the beginnings of the microcontrollers for cell phones. So the ARM9, various versions of ARM9, and especially the ARM11, various elements, various processors from this family became available in order to support, I would say, as the heart of the smartphones. And then the new family with the version 7 of the architecture was introduced to the market, and from the start the family was split not into two but into three branches, the blue, yellow and red branch here. So the branches for embedded applications, so microcontroller and embedded applications, so the branches, then the branch for real-time processing with the Cortex-R family, and the branch for application processor with support for operating system. So memory management unit basically, but for the support for operating system and the support as well for multi-core processing. So some support of the multi-core processing was also added from the start, from the beginning, to the yellow family. In case of of the Cortex-M family, so the family that we are interested in the most, historically everything began with Cortex-M3. So Cortex-M3, so the general purpose, right after the Cortex-M1, so the unwanted child of the Cortex-M family, and then small Cortex-M0, then faster Cortex-M4, again small Cortex-M0 plus, very fast Cortex-M4, M7, and there started the era of 8th version of the architecture, with the onset of the cybersecurity compatible or the course including the cybersecurity, so Cortex-M23, M33, and now the new ones the new ones that are not yet fully deployed, so the M55 and M35P and M35P. So I haven't seen thus far any physical hardware based on this course yet. They do exist already. They do exist since 2 years, maybe 1-2 years, in at least in the descriptions. In case of the application processors, the areas of all three families. So the application processor, all the microcontrollers from the top, from the marked red here. So Cortex A, 8, 9, 5, 7, 15, 50 something, 30 something, 70 something. High-end processors for mobile computing, smartphone servers, etc. So high clock frequency memory management unit. So in general support for operating system, that was that. So that was the application area of the Cortex A. In case of Cortex R, they were from the beginning thought as the processors between the application processors and the microcontrollers, so the embedded processors, offering a lot of processing power. So they were in their idea of the company, they were to replace on the market digital signal processors, mainly produced by Texas Instruments, because they are the main source of DSPs, but not only them. So Motorola did something at these times as well, analog devices and some other smaller branches as well. So that was the idea. So the high performance processors for real-time applications, running at medium frequency, so not as high as in case of application processors with a reduced number of cores, but instead of 4 cores, just two, but with more real-time response. More real-time response. Yet it turns out that family, that something like this is not necessary in the market today. If you want to process data, either use an FPGA. If you want to do it very fast, either use an FPGA or you base on the application processor and the real-time application. So the real-time part you do together with the Cortex-M you base the application on Cortex-M, which is much easier to handle because it has simpler programming model. Yet performance is not very far. It's not very far, so it's not here on this slide. Of course, it's schematically. Take a look how close in performance Cortex R4 and Cortex M7 are. So here it is depicted as if Cortex R7 is faster than Cortex M7, but to be honest, it's not really true. So the difference in performance between R7 and M7 is pretty tiny, and R4 is slower. And of course, it's difficult to compare because on the market there are almost no physical units with Cortex R processor, while there are hundreds of various options we have if we want to use Cortex M7. That's the difference. So in case of Cortex R, the only good thing about Cortex R is that some of them are multiple core units. So we have Cortex R5, Cortex R8, which are dual core units. And because of symmetric dual core units, then we can get more performance. But again, in microcontrollers nowadays, we've got more and more constructions, including more than one Cortex core. Sometimes we have Cortex M7 plus Cortex M4, but that's for the purpose. Those M7 is used for heavy calculation applications, while Cortex M4 is for communication, usually, or for non-time critical tasks. And such a combination of M4 and M7 is really doing a splendid job today. If you want to have more today, there is on the market, there are combinations where there is a Cortex M4 and, for example, Cortex A7. So as well, then we jump beyond the speed or the performance of Cortex-R family, and we take Cortex-A from the beginning. So really on the market, the real time. So this branch, this branch was maybe not a failure, because when I monitor the market, I can see from time to time the process, but not too many of them. And the Cortex-M family, which of course we use today. So the shorter pipeline, lower maximum frequency, yet pretty decent performance, very useful around us. Yeah, stepping back, so a bit of a history still, because all Cortex-M family and Cortex-R family, in fact, they do share the features of the ARM70 DMR architecture. So this was the base of the construction of these two families, of course. So one core, was spread into two large branches. So what is the ARM70 DMI? Historically speaking, what's included inside? So originally it was, of course, a RISC processor, originally for Neumann with 3-stage pipelining only, but with two sets of instructions, 32-bit and 16-bit, and interesting thing, 7 work modes. Of course, operation on 8-bit, 16-bit, and 32-bit data. The TDMI came from the TAMP debug multiplier on board. So the TAMP instructions were included, debug instructions, multiplier, hardware multiplier, and NV block, so the interrupt controller block. All they were added or present inside the structure by default. Today we treat it normally because we have them inside, but again, it was not such obvious than in the past. The pipeline, very simple then, so just fetch, decode, execute, three major simple phases, nothing real special. So something we talked about during the analysis of STM8. So STM8, so yeah, simple pipeline doing some necessary operations. So improving the performance, having to improve the performance. Internally, we did. There was the bank of registers based on, so of course 32-bit registers, so plenty of registers, in fact, because at least theoretically 31 32-bit registers present here, plus the multiplier, hardware multiplier, plus a barrel shifter for single cycle shifting operations, and of course everything calculated on 32-bit arithmetic logic unit. Plenty of signals, of course, to connect, because this is just this is a bus here, and the control signals for the bus that need to be connected if you want to use the core by yourself in your larger design. Something that's really not interesting us at all, unless you want to use this kind of core in your FPGA design. Then you need to connect those pins to necessary signals and necessary lines. Interesting thing, one of the a few interesting things here in this core that made this core very special in those times, and still a bit of interesting from microcontroller's point of view even today. And so the first of those things was the existence of 7 operating modes. In all the other microcontrollers that are available widely in the market, and none of them support so many operating modes. So even Cortex-M's, to be honest, now support just 2 operating modes, but ARM70 DMI, and it was translated to Cortex-R family, they do support 7 operating modes. So we've got the standard user operating modes, but there is a fast interrupt operating mode, normal interrupt operating mode. We have also supervisor, we've got abort mode, we've got privileged system mode, and there is also a 7th mode, which is all the other modes, so undefined. Yeah, those operating modes, they did have some different as well capabilities. Yeah, we'll not get so deeply as Cortex-R is not interesting us, because all this was inherited by Cortex-R. More interesting for us is the history of registers, because the registers part of this, the most important part, is present still in Cortex-M. All of this is still present in Cortex-R, by the way. So in Cortex-M, we've got 37 registers. Out of them, 31 are general purpose and six are status registers. 6 status registers, mind it, not 1, which is normal case, but 6 status registers and 31 registers. Seems fine, seems fine. The problem is, unfortunately, that, here is the register set, is that those registers, out of these 31 registers, in fact, we have available only 13. Why only 13? Because the last register is always treated as a program counter. Then the register, because we must have a program counter, so this is done this way, that there is no program counter, but the program counter is hidden in the register. So a bit of, I feel cheated, to be honest. So program counter and taking one of my beloved register, because I love using registers, and I can't because the program counter is necessary. So anyway, this register is lost, but that's not the worst. The worst is that we are losing, we need a stuck pointer. So the R13 is usually used by convention as a stuck pointer. But this is not the worst. The worst is that we also lose R14, in fact, because we need a link, so-called link register or indexing register, because it's in different microcontrollers. It's named differently. So the register which will be used during the operation with the whole memory, where we have the access, the address access, the access address in the link within the link register. So in fact, we are losing those 3 registers, so they are not in use. So again, why 31 then? Because we have in ARM70 DMI, there were in special operation modes, there were so-called shadow registers. These are the registers with this triangle, gray triangle. So in the system and user mode, this bank of registers was used, and in FIC mode, for example, the additional registers, so all registers from R8 to R14 were shadowed, which means that there was a local copy, which means that's why this is fast interrupt mode. The difference between FIC and ERQ, in fact, the major difference, because in this FIQ mode, during the interrupt service routine, in the beginning of interrupt service routine, there was no need to dump to stack the registers R8 to R12, because they were already shadowed. Shadowing means that they were simply replaced in this mode by the other registers, by a copy of those registers existing in the background. So saving 5 clock cycles for storing for pushing the R8 to R12, and the same amount of time for popping. So it's advantages, definitely. Yet take a look, instead of 31 registers, really we have all those shadowed registers. They are of course added to this fantastic number of 31, but in general we are still left with 13 registers. We are still left in STM8 in ARM70 DMI, and we are left with this as well today, because in Cortex-M7 this mode is not existing, this mode is not existing, there is no such mode, there is no such mode, and there is as well no such mode. We just have 2 modes, which is the user and privileged, not system, but this is the interrupt mode, sharing the same, so having no shadowing register. So what we have today in case of ARM is just one bank of registers. So this is simplified. In Cortex-R, there are still this whole map is still valid. In Cortex-M, no. In Cortex-M, it is simplified. Same with the status register. So we've got 6 status registers, because there is one CPSR and its own shadowed copies. So again, we don't need to, it's convenient because we don't need to store the status register, we don't need to stack it because it's shadowed automatically. But unfortunately, so this convenient solution, unfortunately, is not existing in Cortex-M anymore. So we have to take care about stacking the status register. What is inside the status register in Cortex-M? Status and control, because this is the status, but it's of course status and control, because this part is the status part, this part is was the control part. In case of status part, the most important are first 4 bits with the NZCV standard -0 carry and overflow bits. So the status of the arithmetic logic unit operation, while the control bits variable, but the control bits in general, the bits of controlling the state and the operation of the microprocessor. And we have here the in this ARM7 there was just mode bits, state bits, and enabling and disabling the FIC mode and IRQ. But again, in Cortex-M it's a bit different, slightly. So the bits themselves are a bit different. But more of this already next time. Then we mentioned about the new instruction set, which is the thumb instruction set. And in case of thumb instruction set, there was but maybe before we go there, an example of the instruction set, of the ARM instruction set, because take a look. We talk about 32-bit microcontroller, and it has 32-bit codes. How to put everything, how to combine all the operations and still keep within 32 bits. There are a couple of ideas behind it. First idea is to use as many registers as possible, or to use registers as extensively as possible. So take a look. For example, we've got the multiply instruction, where multiply has 2 sources, 32-bit sources, but the result is 64 bits. So result requires 2 destination registers, and it is done this way, that we've got 1 source register, 2nd source register, 1 destination register, 2nd destination register, only registers, which means that, for example, you can't multiply a register and a number directly. So if you want to multiply a register and a number, first you need to load a number into a register, and then you have to process the register. As well, there are no there are limitations of the length of branches, for example, or limitations of the length of various jams. So the branch, it can be conditional. This is not a problem, because the first 4 bits here means the conditions. So the instruction is executed only if the conditions are true. So if the conditions are met. So this is pretty nice, actually. This was also special. This is also a special feature in ARM, that the conditional instruction in the ARM instruction set. But the offset, where we can jump, the offset from the current location, here it's 24-bit. Doesn't seem so bad. So 24-bit is 16 megabyte. It's 16 megabytes range, which doesn't seem so bad. But remember that here we have 4 gigabyte range. Here we have 4 gigabyte range, and this 16 megabytes. Usually it's enough, but not always. But still, this was pretty nice, because it turns out that despite these limitations, still it can be reduced even further. And then there appeared a thumb instruction set, and in case of thumb instruction set, it was of course shortened from the ARM. And what was shortened? First of all, the registers, accessible registers, were limited from 4-bit to 3-bit. Behind this was that from the 16 registers that were available, 3 of them were occupied as program counter, link register, and stack pointer. which means that why not to add special instructions for accessing those 3 registers, but then registers from R8 to R12 made them no accessible. Okay, but then thanks to this, all the we spare a bit per each register usage. So each time we use a register, instead of 4-bit, it is coded on 3-bit. Then the second important thing is that all the constants or immediate values were shortened down to the very small values. So take a look. This time the branch, which is conditional, does not allow 24-bit range, which is, let's say, pretty okay. But we've got now just 8-bit range, which means that the branching, conditional branching, can be just used to jump plus minus 127 cells in the memory. Because nowadays the third limitation was no conditions. So now this condition is placed only when it is necessary. So it's not that like before, like in the ARM instruction set, that those instructions can be that every instruction, maybe this way, that every instruction can be executed conditionally. Here it's not true any longer. Here it's not true any longer. And then we come to this modified register set. So from the original 36 registers, 31 plus 6, so 37 registers, we end up with a greatly reduced number. So this time, in this operating mode, registers PC, ALR, and SP are just dedicated PC, ALR, and SP, as it should be from the very beginning. We are missing registers R8 to R12 because they are non-available anymore. And then we've got the registers R0 to R7 for normal use. So then, from this very fantastic 31 number of 31 registers, we end up with mere 8 registers. For RISC microcontroller, 8 registers, it's a very small value. So 8 registers is a very small value. Don't forget about it. Still, what it gave us, with all the limitations, it gave us the most important is the code density. Is the code density. Here is an example of the how it looks like in the memory. So in the ARM instruction set, all instructions were 32. Starting with ARM7 TDMI, it was possible by changing the mode in the status register, by the way, it was possible to switch the microcontroller to understand the TUMP instruction set, and then only 16-bit instructions were understood. Thanks to this, we could increase the density of the code twice, and as well speed up the reading from the memory, because as I mentioned, we can read if 128-bit was the interface between the instruction decoder and the memory. So in one reading cycle, 4 ARM instructions could be read, but 8 TUMP instructions could be read. So ARM7 TDMI was a battlefield or test bed, not a battlefield, but a test bed for testing the whether ARM or TUMP instruction set is good. And again, they got some experience from the users, and it turned out that yeah, the idea is not that bad, but it's not possible to use only the TUMP instruction set because this limitation it gives is sometimes too strong. Therefore, finally, in Cortex microcontrollers, the major instruction set is a mixture of TUMP and ARM instructions, and there is no mode switching in Cortex-M anymore. There are only ARM instruction. There are only TUMP2 instruction set with a mixture of 16-bit and 32-bit instructions. For me, it's a chuckle of history, to be honest, because the good thing began. In case of ARM, began with the ARM instruction list. So it was so special, so different from all the other microcontrollers in the market, so that all instructions were had same size. Yeah, and after 10 or even closer to 20 years from the beginning, they go back to where everybody is. So that's okay. There are some instructions which can be 16-bit, like nope. Yet there are some instructions which are must definitely be longer, like for example various branches. So that's why 32-bit. And today we've got a mixture. They've got a mixture, and in general, the mixture gives us a gain of about 30% in case of code size and in case of performance, and that's why they decided to go in Cortex-M family with TOM2 and to neglect the switching of the modes between those two instruction set. So they found out which instructions would be the most useful in the 32-bit version, which of them in a 16-bit version, and this mixture is the TOM2 instruction set, which is present today, which we're using today widely in Cortex-M. By the way, interestingly, take a look, 64-bit, right? So the 64-bit architecture, but the instructions, surprise, surprise, only 32-bit. So again, 64-bit processor, not really. So that's the ARM. So it's just 32-bit from the top to the bottom. In case of ARM7 TDMI, there appeared also memory control systems. So it is called virtual memory system. So the ARM7, it was a bit more than a microcontroller, therefore the virtual memory system appeared. The virtual memory systems are important, and two versions of this virtual memory system appeared. So this is the so-called MPU and MMU. So virtual memory system is known today as the memory management unit, and the protected memory system is called memory protection unit today. What's the difference? So it appeared, so we don't have again, if we have some time, I will get back to the functionality of those systems, especially to the functionality of the MPU, as this system is actually used in microcontroller. Because what's the difference between those two systems that appeared, those memory control systems? Maybe simpler one is MPU. So briefly, what's the MPU? MPU is the protection. So we can set a privileged process. So the process, for example, the operating system, or some, I don't know, in main loop, we can protect certain areas against unwanted access or against villain access. This is not about security, because it's not about protecting against some anonymous group attacking. This is more about protecting against other tasks. So for example, we can protect the access to some hardware peripherals, so that it only, and give the permission only to one task, for example, to ADC converter, and give a permission to work with ADC only with one task, and all the other tasks are to be blocked. Or we can protect a certain piece of code so that it's protected against unwanted overwritten, against being overwritten accidentally by some other existing tasks. So this is only this. So this is the MPU. The MMU, or virtual memory system, is a bit different. So here, depending on the PID of task, the memory it wants to reach is translated into some physical memory, giving us a chance, giving operating system especially a chance to enclose tasks in their own bubbles, with their memories always starting from zero and theoretically overlapping onto each other. In practice, of course, the memory planning is critical here. Also, the good thing about the memory management unit is that various types of memory can be used for this purpose, as you know from Linux or Windows, where the MMU works in the background beautifully. It has to be, of course, very fast, not to slow down the access to such memory. That's why it's a hardware system, and that's why the MMU is pretty complex, and that's why today in microcontrollers we doesn't simply have it. So there is no MMU in the microcontrollers. We have just MPUs, and MPUs we do have for protecting, self-protecting, because the MPU is for self-protecting actually of the resources. The MMU itself is too complex and it's not available in microcontrollers. So the operating systems have to use the simpler MPU, and that's why also the general purpose operating systems is very difficult to be ported to microcontroller, because the general purpose operating systems require MMU because of the high amount of tasks executed and high memory requirements, and the MMU is really a must here. We don't have must MMU at the moment in ARM Cortex-M microcontrollers. Maybe it will change, but so now it's missing. So ARM70 DMI, yes, and if you want the MMU, you have to take Cortex-A. So Cortex-A, okay, but in case of Cortex-M's MPU, yes, MMU, no. The thing that, to be honest, it's a bit boring, and the thing that we need just to mention are the buses inside. Are the buses inside the microcontroller, inside the Cortex microcontroller. Let's speed it up a bit. It's pretty boring and not that useful, fortunately. We don't want to implement the core. We just want to use the microcontroller of the core already implemented. That's why the particular knowledge about the protocols, about the signals, about the timings on the buses is not important. What's interesting and what's worth to know is that in one microcontroller, Cortex and microcontroller, we usually have couple of buses. And the structure may be a bit different. So sometimes we have, usually the peripherals, so the CPU is the source of the buses. So usually it's not this architecture that you can see here, where there is a core with just one bus and there is a bridge where another bus is translated by the bridge to the main bus. Usually we've got the structure today. Such architecture may happen, but usually we have a structure that from the microcontroller we've got AHB, for example, 1 and AHB2 bus, or AXI, or APB bus. But usually the buses are connected directly to the CPU, and usually the CPU has. Sometimes we have a configuration with a bridge translating to the slower buses. Sometimes we've got the configuration where everything is connected directly to the microcontroller, thus simplifying the construction of the microcontroller itself, because the bridge then is not necessary, because the bridge is included in a CPU, in a microprocessor. So usually we have, in case of microcontroller, a couple of different buses. In case of Cortex and microcontrollers, the buses are, there may be 2, 3, 4, 5. So really, the numbers are growing. The larger the processor, the newer, the larger, the more buses does it have. But it's done a bit on purpose, those different buses, because today it's not really possible that the transmission is enclosed just within a single bus, which does mean that the transmission can go from here to here and from here to here independently within a certain area, within a certain bus. Therefore, in order to speed up, increase the performance of the whole core, there are more and more buses being added, and today we've got some of them present. Some examples about internal structure of the buses already, if not next week, because I don't know if we have enough time. Probably in 2 weeks' time, we'll try to analyze the bus structure of some simple, medium-sized, and large microcontrollers, and you'll see by yourself how it looks like about the buses, various buses. So we have the in case of this AMBA system, because the AMBA system is the advanced bus architecture, advanced microprocessor bus architecture. So that's where it comes from. It's also a standard, let's say, from microcontroller from ARM. So it's not a standard, but it's treated as a standard. So there are some external companies also implementing in their own applications the AMBA system. In this AMBA systems, we've got a couple of families of buses. The most important are, from our perspective, the AHB, so high-speed bus, the APB, so the peripheral bus, so the low speed, and simpler bus, and as well the AXI. AXI is the top bus, the high performance bus with higher performance than AHB, available in especially in microcontrollers described in documents version 8. I'm saying about Cortex-M because AXI was introduced earlier for Cortex, Cortex-A and Cortex-R. But we'll get back to this on some examples because, as I mentioned, it's pretty boring and pretty useless to analyze so deeply, profoundly those elements. Good. That's it for me for now for today, because we've got now more details into Cortex-M already, not ARM7, not AMBA, but Cortex-M. But we have just 2 minutes, so maybe some questions from your side. If no questions, unfortunately, next week remotely again. Let's hope this finishes at long last. But as of now, we must stay online. So next week again, 11:15 online meeting on Zoom. Yes.
Do you know maybe how will the exam look like? If it will be online or stationary?
No. The exam. In the regulations formally, at least there is a green light for the exams. So the exams are to be conducted live at the university. So the exams, the first term and the second term, they will be conducted at the university, not online this time. Any more questions?
I wanted to ask, with whom can we talk in order to ask about this remote and stationary classes question? Because for us, we have big problems because later we have another class, and then I have to do this online class in the library or somewhere in school, in the university, because otherwise we don't have time to move.
You can contact the Mrs. Agnieszka Misiewicz. Okay. She's sitting in room 208. So actually, if you go to this room, you can ask anybody because there are a couple of guys and girls there sitting. They are or taking care about the classes, various didactic issues. So you can go there and ask them, and then they should help you. If not, they will ask the dean Piotrowski, because he's responsible. He's their boss, in fact. And but this is the task team dealing with classes. So you can ask them. Okay, it's room C5 280, if I'm not mistaken.
Okay, thank you.
You're welcome. Any more questions? If no, thank you very much for today. Have a good day. Still, see you next time.
Thank you. Goodbye. Have a good day.
Have a good day. Bye-bye.
Bye.